In this video, we'd like to draw all electrons of the following elements using the simplified Bohr model of the atom, just showing the different energy levels that electrons can occupy, and we want to connect that with the periodic table as well. Here we see that hydrogen is the first element of the periodic table. It's in the upper left, and it has one proton. If hydrogen is to be neutral, it would have to have one proton and one electron so that the positive proton balances with the negative electron. So that's what we want to draw first for hydrogen, just one proton in the nucleus. And then outside the nucleus is an electron. And the electron is in the first energy level shell, it's called. You could call it n equals 1. The next element is helium, and helium has two protons in its nucleus. Therefore, in order to achieve equilibrium, we want to have two electrons in that first energy level shell. And the two negatives will cancel with the two positives, making it overall neutral. But we are still in the first energy level shell. Now, helium on the periodic table here, you have to jump across to the other side to see it. In order to go to the next element, which is lithium, we're going to have to go to a new row. And that has significance when it comes to the electrons that are around helium. See, helium can hold two electrons in its first energy level shell, but that is actually all that that first energy level shell can hold. It has a max of two. When we go to the next row in the periodic table, that means we're going to actually go to the next energy level shell when we add another electron. So here we're in row 1. So row 1 corresponds to the first energy level, but row 2 here, these electrons will actually be in the second energy level. So we're going to need another ring, is what this means. Lithium will have 3 protons in its nucleus, and that first shell is going to be full, and it's going to have only 2 electrons in it, and that's all it can hold. In order to get a third electron in here, we're going to have to create a new shell. In the Bohr model, that just means adding another ring. All right, so our first shell here is called n equals 1, and the next shell is the second energy level, which we can call n equals 2. That electron there is in that second shell. Now the thing about the second level is, on average, the electron's going to be farther away from the nucleus. And it's all alone out there. And what that means is it's actually going to be very easy for it to be stolen away. Like, for example, if some other positive particle were to come near the lithium atom, the electron here would be highly attracted to that positive particle. It could potentially be stolen away by another positive particle, is the idea. And so lithium ends up being extremely reactive, meaning that it can interact with other compounds and other elements very readily because that electron can be stolen so easily. Let's look at beryllium next. Beryllium will have 4 protons in the center nucleus. Once again, that first energy level shell is going to be full with just 2 electrons. But if we want balance, we need 2 more electrons. Then we'll have 4 protons and 4 electrons. But they have to go in that second energy level shell. So it'll look like that. So we're now here at beryllium. We're going to make a leap across to boron next. And for that, we just have to add one more proton to have 5 protons, and we'll have 5 electrons as well. So let's draw 5 protons in the nucleus. We will fill our first shell, and now we need 3 more electrons. Now you might be thinking that perhaps the second energy level here is going to be full with 2 electrons as well, because that's how it was for the inner shell. Turns out that's not the case. That second energy level, we say, can hold up to 8 electrons in the Bohr model. So we just have to add one more electron to it. As you can see now, we've got 2 electrons in the inner shell. We've got 3 electrons in the outer shell. And so that's the complete diagram for boron using the Bohr model. Here's n equals 1, n equals 2. All right, now we're going to try carbon. So according to the periodic table here, carbon has 6 protons in its nucleus. So we just want to draw that. Fill the first shell with just 2 electrons. And we now want to have 4 electrons in the outer shell. So carbon's a special element that it has 4 electrons in its outer shell. We'll see why that is in the future. It can bond with many, many different things in many different configurations, and it is an important element when it comes to life. Let's take a look at nitrogen next. Nitrogen will have 7 protons in the center. Okay, we'll draw the inner shell, and we want just 5 electrons in that outer shell. So 5 in the outer shell plus 2 in the inner shell makes a total of 7, and then we have balance electrically. All right, oxygen has 8 protons. All right, so we'll have this. Let's put 6 electrons in the outer shell. All right. Now fluorine. If you look at the periodic table, you can see that fluorine is the second to last element there. It's got 9 protons. And we'll do 7 electrons in the outer shell. All right, that brings us to a special element, neon, which is at the very end of the periodic table. Now, it's significant to be at the end, and what it means in this case is that neon is going to have a full outer shell of electrons. That second shell can only hold 8 electrons max. And so neon will actually have all 8, as we'll see here. 10 protons in the nucleus for neon. Two electrons in the inner shell. 8 electrons in its outer shell. And we would call that just a complete outer shell. And so what would we do next if we needed to go to the next element? We'd have to go to the next energy level, which is n equals 3, and this is the element sodium. Sodium has 11 protons in the nucleus, and it's going to have 11 electrons. So let's look at that for a second here. Sodium, element Na, has 11 protons. So there's 11 protons. We'll fill that inner shell. That's a complete inner shell. And we're going to put 8 electrons in the second energy level. And that is a complete shell as well. So we have 2 electrons in the first energy level. We've got 8 electrons in the second energy level. And that's a total of 10 so far. We need one more for sodium. And so where is it going to go? So since that second energy level is full, we're going to put our remaining electron into the third energy level, like that. So this is the n equals 3 energy level. Now, in a similar way to how I had said that lithium has an electron that could be easily stolen because it's kind of on its own out there, same kind of thing can happen with sodium. And we find that even though sodium is a much bigger element than lithium, they will actually behave chemically in similar ways. For example, they both will readily donate an electron in a chemical reaction, as we'll see. Let's draw the Bohr model for a few random atoms in the periodic table here that we haven't covered yet. Aluminum. Aluminum is element number 13. It has 13 protons. So if I don't want to draw every proton, I can just put plus 13 as the nucleus. So there's supposed to be 13 protons in there. I can draw 2 electrons in the inner shell. We'll want a full second shell. Now, how do I know that? Because, well, we need 13 electrons for a neutral atom, so I'm going to need at least 10 here. Okay, that shell is full. We can actually count up here 1, 2, 3 electrons in the third energy level. So let's just draw those. Okay, there's a good picture of aluminum using the Bohr model. So chlorine is similar to aluminum, but it has, let's see, if we count them, 1, 2, 3, 4, 5, 6, 7. You can actually count the electrons in the outer shell if you just count across the row. So chlorine's going to have 7 in its outer shell. It is element number 17, so it has 17 protons in the nucleus. We know it has a full first shell. Maybe I'll use a different color here. We know that it has a full second shell as well. And now we'll go to the third energy level, and we just want 7 electrons in that third energy level. Now, one thing to point out and keep in mind here is that atoms want to have a complete shell if possible. Like chlorine, for example, would rather have 8 electrons in its outer shell than 7. And so what that means is that whereas an atom like lithium tends to donate an electron that it wants to get rid of, chlorine here will actually attract an electron. So it could have a complete outer shell. So it's not totally happy right now because it's got 7 electrons, but it wishes it could have 8. And we'll see shortly how lithium and chlorine could come together and react chemically where lithium will donate an electron to chlorine. That way lithium will be happy because it'll have just a complete outer shell and no electron on the outside there. And chlorine will be happy too because it would have a complete 8 electrons in that outer shell. All right, we want to draw what's happening with calcium here. So calcium is a bigger atom. It's got 20 protons. So we're talking about going to the 4th energy level here. So let's do plus 20 for the nucleus. And we want to draw the electrons in the inner shell. But I think just to save time, I'm just going to draw the rings here, and I'll assume that they're filled. We know the first energy level is filled, we know the second energy level is filled, and we know the third energy level has to be filled too as well for calcium. And so what really ends up mattering the most when it comes to chemical reactivity is the electrons in the outer shell. So how many electrons would calcium really have in the outer shell? We see that the new row has just started. We've got potassium being the first element in it, and now calcium. So that means that it's got 2 electrons in its outer shell, because you count from the left, 1 in the outer shell, 2 in the outer shell, and so on. So these are called valence electrons, the electrons in the outer shell. And they are what matter most when it comes to how these elements will interact with other elements. Okay, so calcium, it wants to get rid of 2 electrons if possible so that it could have a complete outer shell. And we'll see later how calcium will donate those 2 electrons to other things in order to have that balance. And that's where a type of chemical bonding will occur. All right, so when it comes to titanium here, so titanium is found in a special region called the transition metals, and things get substantially more complicated when we get to that region. So for all the way up to calcium, things are fairly straightforward. We just want to fill the different energy levels, and once they're full, we go to the next energy level. But here it gets more complicated. In a future video, we'll go into exactly how titanium's electrons are placed in the different energy levels. But for now, I'll just draw what the answer would be. What happens with titanium is you've got a full inner shell, 2 electrons there. You've got 8 electrons in the second energy level. And then you would start to fill that third energy level with 8 electrons. So far what I have is the electron configuration for argon. This is 18 electrons, 2 in the inner shell, 8 in the second shell, and 8 in the third shell. And I said that in order to make calcium, we would just add another energy level, which would be called n equals 4. And then we would put those 2 remaining electrons in that fourth energy level. With titanium, those 2 electrons will go there. They will go in the outer shell. But here's what's a little weird. The next 2 electrons do not go in the outer shell. They end up going in the third shell. So let's make room for them. And now we've got actually 10 electrons in that third energy level and 2 electrons in the outer energy level. This gives us a total of 2 plus 8 plus 10 plus 2. That is 22 electrons. Now, we don't have to go into all the reasons why that is what it is. Most of the diagrams you'll be making will be calcium size or smaller. And when you deal with calcium, you just have to remember 2 for the inner shell, 8 for the second shell, and then 8 for the third shell. It's only when we go beyond calcium and into the transition metals where we start having to add the electrons in complicated ways. We'll get to that in a future video. So just to compare titanium to calcium, calcium would be 2 plus 8 plus 8 plus 2. And as you can see, we've added the 2 remaining electrons here to the third energy level instead of the fourth. I don't want to throw too much at you at once here, so we'll just say that it gets complicated after calcium for now. And in a future video, we'll cover exactly how to do that.